Okay, so there are a few things to discuss to finish off our discussion of Schrödinger and Heisenberg pictures. So the first thing is, you'll notice that I labeled operators to say whether operators belong to Schrödinger or Heisenberg picture, but the one operator that I did not label is the Hamiltonian. Why didn't I label the Hamiltonian? Okay, well, let's work out what the Hamiltonian is at time t. And to work out what the Hamiltonian is at time t, I should take e to the minus iht times the Hamiltonian e to the minus iht. So I'm using here just the time evolution rule that you see of the Heisenberg picture. Now the point is that because the Hamiltonian commutes with itself, I can pull the Hamiltonian through the e to the minus iht to obtain what I've written down. But then the first exponential times the second exponential just gives me 1, and I'm left with the Hamiltonian. So actually, the Hamiltonian doesn't evolve in time, and the Hamiltonian in Schrödinger picture is equal to the Hamiltonian in Heisenberg picture. Now, that's not true for every picture, but it is true for Schrödinger and Heisenberg picture. So if I'm just flipping between Schrödinger and Heisenberg picture, I don't need to tell you which picture the Hamiltonian belongs to, because it's the same in the two pictures. If I was using interaction picture, I would need to be a little bit more careful and start specifying which Hamiltonian I am considering. So that's the first comment that I wanted to make. That's why I haven't labeled which picture the Hamiltonian belongs to, because the Hamiltonian in Schrödinger picture is equal to the Hamiltonian in Heisenberg picture. Next, you see in Schrödinger picture, we had a nice equation of motion that the states obey, okay? So in a Heisenberg picture, we should also have a nice equation of motion, but now it will be the operators that obey that equation of motion. So I would just like to work out what that equation of motion is. So what is the Heisenberg equation of motion? So let's take IH bar d by dt, and now instead of acting on the Schrödinger picture state, let's act on the Heisenberg operator. So we'll take OH of t. And just for this exercise, I'm going to put all of the H bars back in again. So we've got IH bar d by dt. Let me put the H bars back into this formula. Good. And we've got e to the iht over h bar. We've got the Heisenberg operator at naught. Then we've got e to the minus iht over h bar. I am going to assume that our operator has no explicit time dependence. So when I act with d by dt on the first exponential, well, that's an easy derivative to calculate. We will just get IH over h bar. And then we've got e to the iht over h bar, OH of naught, e to the minus iht over h bar. Then when it acts on my operator OH, well, I don't need to worry, because I've said that OH has no explicit time dependence. But then when it acts on the final exponential, so I leave the first exponential alone, I've got OH of naught, I've got the second exponential, and differentiating that second exponential, I will get minus IH over h bar. Now, I can happily pull this last factor, the minus IH over h bar, through the exponential, but I cannot pull it through OH of naught because the Hamiltonian and my Heisenberg picture operator need not commute. So I must leave the Hamiltonian to the right-hand side of OH of naught in the first term, and I must leave it to the left-hand side of OH of naught in the first term, and that is because the commutator of the Hamiltonian with OH of naught need not vanish. So I cannot pull my Hamiltonian through OH of naught. Okay, so now looking at the first term, well, I times by I will give me a minus. H bar divided by H bar is just 1. I've got the Hamiltonian. And then recognize that this term over here, that whole thing sitting over there, is nothing but the Heisenberg picture operator at time t, and I can make the same observation for that piece sitting over there. So I'll have minus IH, and then it will be multiplied by OH of t. For the second term, I've got plus, so I've got OH of t. Then I've got the I sitting up front times the minus I. Well, that's a 1. I've got the H bar divided by H bar, so that's nothing. And then I've got the Hamiltonian sitting there. So what do I have? I have the commutator of OH of t with the Hamiltonian. And this is the Heisenberg equation of motion. It tells me that I, H bar, the derivative of the Heisenberg operator with respect to t is equal to the commutator of the Heisenberg operator with the Hamiltonian. Okay, so that is the Heisenberg equation of motion. It's an equation for the operators of the theory. Let me maybe just write down that the Heisenberg picture kit doesn't evolve in time. Oh. So there we are. Okay, good. Let me just now clean a little space. Okay, so we've learned that our Schrodinger picture operators evolve in time. The Schrodinger picture operators don't. The equation of motion for the states is just the Schrodinger equation. We've learned that our Heisenberg picture operators evolve in time. The equation of motion for our Heisenberg picture operators is the Heisenberg equation of motion. It tells us that IH bar times the derivative of our operator is the commutator of the operator with the Hamiltonian. And then finally, the Heisenberg picture states don't evolve in time. Good. Now, why did we do this? We were trying to learn something about translations. The fact that there is a Heisenberg picture and a Schrodinger picture is telling you that either you can time translate your states or you can time translate your operators. And notice something. If I write psi of t, Schrodinger picture, is equal to u of t, psi of naught, in Schrodinger picture, then our operator u of t is equal to e to the minus I h t, and I'm not putting in h bar anymore. So that's how states evolve. Now let's look at the Heisenberg picture where operators evolve. If I rather want to evolve the operator, I should evolve it with u dagger of t. So remember, okay, so let's just write down the rule. If this is u of t, then for u dagger of t, it would be e. I should take a complex conjugate. Complex conjugate of minus I gives me I. H dagger is h, and complex conjugate of t is just t. So if you look at the Heisenberg picture evolution, I've got u dagger of t, o, u. So what I want you to compare, if the operator u produces the evolution of the states, so this is the rule for the evolution of the states, then For operators, I have this evolution. So the same operator appears. It's again U, this unitary operator U. But if it's U that produces the evolution of the state, then it's U dagger operator U that produces the evolution of the operator. This is an extremely general rule. So what we will find is other symmetry transformations. For example, the Lorentz transformation, that will also be represented by a unitary operator. And we'll be able to give the Lorentz transformation as a transformation of the states. Written as a transformation of the states, it will look like U of lambda for the Lorentz transformation on the state, or we will be able to realize it as a transformation of the operators. And on the operators, it will act as U dagger of lambda, the operator U of lambda. So you always have this freedom to implement the transformation on states or on operators. And this is always the relation between those two transformations. Okay, good. That was what I wanted to discuss about Heisenberg and Schrödinger pictures.